Hey guys, okay, so this is the start of our new material. Not really new, it's kind of more review still, like from chapters 1 through 3. But we're going to be starting solutions and aqueous reactions and stoichiometry chemistry. Okay, so we're going to start with section 4.1. You'll see right out the gate, there's some definitions that I would expect you to know. Solution, solvent, you remember solute, all of these things are old news. You learned these last year in honors chemistry. But there's a few new ones that may not be as intuitive or you may not remember, and those are electrolyte, a non-electrolyte, and a dissociate, okay? So an electrolyte is a solution that actually contains ions, okay? If we remember, ions are going to be your cations and your anions, and because there's cations and anions inside of the solution, it's going to conduct electricity, okay? This is because of the transferring electrons between the sodium ion the cation and the anion, okay? So an example of this would be salt water, okay? Sodium and chlorine ions will be present, therefore salt water will conduct electricity, okay? So salt water or sodium chloride is an example of an electrolyte. A non-electrolyte is a solution that does not contain ions, okay? So no dissociations occurring, and the solution will not conduct electricity. So like for example, sugar water. Sugar is a covalent compound, therefore it's not going to break apart, it's just going to dissolve in the water, and we'll look at an example here in a second. And then the last thing that I need you to know is a dissociate, okay? Dissociate, or break apart, okay? And that is when an ionic compound, when it dissolves in solution, breaks into its anion and its cation. So the example that I have here, I eliminated water, okay? But since this is aqueous, aqueous means dissolved in water, we can assume that water is present. So what happens is, I guess I should have put solid here, sodium chloride, when we dissolve it in water, is going to break apart into sodium and chlorine. Okay, so those are the definitions that you need to know from section 4.1. Also, number 2 here, what is water's role in dissociation? Okay, so with this example that I gave up here, I just kind of said we just assume water is present. So what is water's role? So we need to remember that water is a polar molecule, okay? And we have to remember when we're talking about polar and nonpolar things, we have to discuss their electronegativities, okay? You have to remember that electronegativity is the atom's want of electrons when it's in a covalent bond, okay? And if you remember our trend, the more protons an atom has, the more likely it is to pull the electrons close to it, okay? So for example, as I move from left to right across the periodic table, my electronegativity is going to increase. And if we remember, fluorine has the highest electronegativity at 4.0. Okay, so everything else kind of falls underneath that 4.0. So if we're going to be talking about water as a polar molecule, okay, we have to remember what water looks like. Water is oxygen with 2 hydrogens attached to it, okay? And more or less they're attached through covalent bonding. Okay? But since oxygen is further right on the periodic table than hydrogen, it's going to be more electronegativity, or more electronegative, meaning that it wants the electrons in the bond more than hydrogen, okay? So this unequal sharing of these electrons is what's going to cause these partial charges on our covalent compound. Now, here's the thing. These aren't full charges. They're not full charges because the atoms are not fully losing and gaining electrons. They're only partial charges because there's sharing involved, okay? So since oxygen wants the electrons more, oxygen will be partially negative, where hydrogen will be partially positive, okay? And this is where we can say that water is a polar molecule because the oxygen side of the water molecule is going to be more negatively charged, where the hydrogen side is going to be more positively charged. Okay? So that is why water is a polar molecule. Okay? This is, again, review. Cations are positively charged ions. These are going to be our metal ions, elements to the left of the staircase. Anions are negatively charged ions. These are our nonmetals. They're going to be to the right of the staircase. And since water has these partial charges that I talked about, it can act like a magnet towards cations, and this should say anions, in solutions. Meaning, the negative side of the water will be attracted to a cation, and the positive side of water will be attracted to anions. Okay, so that's that. So here's an example that I would like to show you. Okay, let me kind of zoom in here for you. And your book does a really good job of showing this as well. But you'll see, here's my sodium and my chlorine, my sodium and my chlorine. Here comes the positive side of the hydrogen coming in to surround the chlorine. And what you'll notice is it's going to pull the chlorine away from the solid ionic structure. Okay? Same thing. The oxygen, which is partially negative, is going to come in and surround the cation, which is sodium, and pull it away. Okay? And so this would be the solid, and this is the dissolved. So this is what it's going to look like in a dissolved solution when you have an electrolyte present, like sodium chloride. Okay? And then the last thing that I want you to know is solvation. Okay? And solvation is just the stabilization of cations and anions in water solution, which means that the water solution breaks apart the cations and anions, and then you have a solution that has a solvent and a solute present. Okay? Third point. So far we've talked about what does it look like when ionic compounds dissolve. Now we need to talk about, well, what about the, where'd I go? Now we need to talk about if the molecular compounds and why they don't form electrolytes. They're considered non-electrolytes. So if molecular compounds don't dissociate, like they don't break apart like our cations and our anions, how can they actually make a solution? Okay? So in solutions, molecular compounds will remain intact and continue to share electrons through covalent bonding. Okay, so they're not going to break apart. Molecular compounds can have other interactions that do not involve dissociation, and we'll get into these interactions when we get into Chapter 11. But for now, all I need you to know is that molecular compounds are considered non-electrolytes because they don't break apart. Okay, and you can kind of see here, let me zoom in on this for a second. So all of these red and white guys over here are my water molecules. And these are like sucrose, okay? And what you'll notice is that the water molecules are kind of having an interaction with the whole molecule and pulling it away from the other molecules from the solid structure, okay? This looks different than this one, right? Because you see the chlorine and the sodium separate. Down here, the molecular compound stays intact and the water just kind of surrounds it to pull it away from the solid compound. Okay, so that's how water molecules, or I'm sorry, not water molecules, covalent compounds dissolve, and that's why they're considered non-electrolytes, because there's no positive or negative charge present. Okay, so what is the difference between a strong and a weak electrolyte? Okay, this is kind of the last thing that we need to talk about. The difference between a strong and a weak electrolyte is with a strong electrolyte, the solute that exists in solutions is completely all ions, okay? So examples of these things would be like sodium chloride, hydrochloric acid. There is only a forward reaction, meaning once I go from HCl to H plus and Cl, okay, because this is a strong acid, okay, there's no going back. Chlorine and hydrogen in water will not go back together, okay? And we indicate this by just a forward arrow and no reverse arrow, okay? A weak electrolyte is a solute that exists in solutions that only have a small amount of ions present, okay? So acetic acid here is my example. Acetic acid, if I can draw this, will dissociate in an aqueous solution, but only partially. So now I have a reverse arrow indicating it's a reversible reaction, so I can go back to a full acetic acid compound, okay? So that's the difference between weak and strong. So things that you need to know is you need to know your strong acids so you can tell me that those are considered weak electrolytes and you have all ions in solution. Okay? So this is all that I have for you for section 4.1. In class, we're going to do numbers 1 through 4. If you want to go ahead and take a jab at 11, 12, 15, 17, and 18, that would be great for tomorrow's class. Thanks, guys.